Hello everyone. So today we are going to do a very brief walkthrough of our exam 3. So I haven't start grading the exam yet, but I think overall, at least based on what I went through, the first several questions, and also the first three questions of the calculation problems are they went it went pretty well. The fourth one is a little bit tricky. So maybe let's start with the short questions first. So for short questions, the first is asking you what is the critical Reynolds number. And we said that RE critical or critical Reynolds number is a transition between laminar flow to turbulent flow. That should be sufficient. And if your RE is smaller than the REC, it's laminar. And if it's RE larger than REC, it is a turbulent flow. Okay, that's the first short question about the critical Reynolds number. The second one is to ask you to name a difference between laminar and turbulent flow. One very straightforward one, as we said, is for laminar flow that your RE is smaller than REC, and for turbulent flow is your RE is larger than your REC. And at the same time, laminar flow is supposed to be organized, smooth, and your turbulent flow is supposed to be fluctuated and chaotic. So as long as you pointed out this major difference, you're good. For the third short question is the continuity equation about mass balance and energy balance? Continuity equation. And this continuity equation we have mentioned, it's a mass balance. So that's it. The fourth one we're asking in Navier-Stokes equation, V is written as UI plus VJ plus WK. And it asks like what are the U, V, and W. And we have talked about in the repeatedly in the class and all in the lectures and also in our examples given in the class that U, V, W are velocity on X, Y, Z, or I, J, K directions. And the fifth one, it's asking how does RE change with pipe diameter? How RE changes with pipe diameter D when you have a fixed Q. If you still remember, this is an example we gave in the last lecture. So RE is written as rho v d over mu, right? Theoretically, if v is fixed, if you increase your d, your RE will increase, right? But right now is our Q is fixed, and your V is a function of D. So we need to know how VD changes with D, right? And then we can determine how RE changes with D. And in the class, we said that V equals Q over A equals Q over pi over 4 d squared, right? So it equals Q 4Q over pi d squared. So your V is proportional to 1 over d squared. And so V multiplied by d is proportional to 1 over d squared multiplied by d. So it's proportional to 1 over d. So your rho and mu are the same. So your RE should equals to rho VD over mu is proportional to 1 over D. So when your D increase, you will have your RE decrease, right? And then we start to enter the first calculation problem. It is, let me see, we are given the velocity field. We have our u equals x squared plus y squared plus z squared. And our v equals xy plus yz plus z. And we are asked for what does w equals to, right? What does w equal to? So it's very straightforward, and I put it there too. It should be about continuity equation, right? And we are given it's steady flow, which means we can directly get this equation: du over dx plus dv over dy plus dw over dz equals 0, right? And du over dx, we have stressed it several times, it should be only related to with derivative to x, right? So du over dx, the first term 2x, x squared is a function of x, so the derivative of this term is 2x. And y squared is not a function of the second term, y squared, is not a function of x, so its derivative is 0, the same as the third term. D squared here is not a function of x, so the derivative of d squared to x is 0, so it equals to 2x. And next is dv over dy. So the first term, xy, is a function of y, and derivative of x is y. Derivative of xy respect to y is x. And the second one term is yz, and the derivative of yz to respect to y is z. The third term is not related to y at all, so its derivative is 0. So it equals x plus y. Okay, and then we plug in du over dx here becomes 2x dv over dy. We add x plus y plus dw over dz should equal 0. So dw over dz equals negative 3x minus here I wrote it wrong. Here is z. Here should be z minus z. Okay, right now we need to integrate this term. So we integrate on both ends. So the left hand becomes w. So it equals negative 3x. Integrate over z is negative 3xz minus 1 over 2z squared. And don't forget, this one we did integration over z, right? So we should add a function of x and y, right? So this should be the final answer. W should equals negative 3xz minus 1 over 2z squared plus the function of x and y. Okay, a very straightforward application of continuity equation. The second one is about, let me check, Bernoulli equation. So it's a flow through a narrow area and then expand again, right? And it asks like the pressure difference between 1 and 2. And we know that D1 is here, 0.1 meter, and D2 is here, which equals 0.06 meter. And we are given that Q equals 0.05 meters square per second. A lot of you have a question is the density the same throughout the process? I think it's pretty straightforward because although I didn't talk about it, but we directly kind of point you to Bernoulli equation, right? B equation. And one of the underlying condition of Bernoulli equation is the fluid is incompressible, which means rho is a constant. Another question I was asked was, is Q changing from 1 to 2? So I think right now, out of this kind of exam mode, you may think it better. So Q should be constant everywhere. Everywhere. And why is that? Because of that, your rho is constant, right? And we said that m dot, the mass flow rate, should be same everywhere due to mass conservation law. Okay, so Q equals m dot over rho should be conserved everywhere, right? Okay, you see that we know Q, right? And we actually, in the class, we have derived Q in one of the question, in one of the problems we gave in the lecture. We were given that Q equals A2 multiplied by the square root of 2 P1 minus P2 over rho multiplied by 1 minus A2 over A1 square. This is what we derived by ourselves in the lecture. So right now it's okay. Originally we were given the pressure difference and we need to calculate the flow rate Q. Right now is we know the flow rate Q, we want to calculate the pressure difference. And we just need to reformat this equation. And what we will have is P1 minus P2 equals Q square multiplied by rho 1 minus A2 over A1 square divided by 2A2 square. And let's see what we know and what are unknown variables here. So Q constant, which is given. We know it. Rho, we are given as G. So we know as G. So we can consider as a known variable too. And A2 and A1, because we know D2 and D1, it can be considered known variables too. So it seems like everything are given. We just need to plug in all the numbers to do the calculation. So let's first calculate rho. Rho equals Sg multiplied by rho water, H2O. So it is 0.885 multiplied by 1,000 kilogram per meters cube, which means the density of the fluid in such a Venturi system is 850 kilogram per meters cube, right? And the area ratio A2 over A1 equals D2 over D1 square. And we know that D2 is 0.06 and D1 is 0.1. And we plug in all the numbers, what we have is 0.36, right? So when the Q equals 0.05 meters cubed per second, we plug in all the numbers to this equation. We will have P1 minus P2 equals 0.05 square multiplied by 850 multiplied by 1 minus 0.36 square divided by 2 multiplied by pi over 4 multiplied by D2 is 0.06 square. And what we have now is 1.16, or I see some of you calculate as 1.15 multiplied by 10 to the 5 Newton per meter square. So also you can write it as 116 kilopascal. Okay, that's for this Bernoulli equation problem. Some of you were asking why we were given Q larger than 0.005, smaller than 0.05 meters cubed per second. So you should notice that your delta P, pressure difference, is proportional to Q squared. So if your Q changes, such as your Q increases, your delta P pressure difference should increase too. So originally in this problem, you were asking that if your Q is in this range, what should be your delta P range? And then I feel like it's just a same calculation, and it will take a longer time. So I revise it to be that your Q equals a fixed value here. Okay, that's about the Bernoulli equation. Okay, the third one is, let me double check. The third one is about the laminar flow and turbulent flow. Okay, it's very similar to what we covered in the last class. The only difference I think is you need to use the ideal gas law to calculate the first question. So in the first question, it's asking use ideal gas law to determine the density of air. And in this specific book, we said that we always use that P equals rho RT as the ideal gas law. And rho is something we don't know, but R is given. T is given as 366 Kelvin, right? And R is given as 287 joules per kilogram multiplied by Kelvin. And P we were given as 1 atmospheric pressure, which is 101,325 Pascal. So we can calculate the only unknown variable rho here equals P over R and T. So it equals 101,325 Pascal over 287 joule per kilogram multiplied by Kelvin multiplied by 366 Kelvin, which is 0.965 kilogram per meters cube, right? So that's the density we calculated. We solved the first problem. The second problem, it has to determine the minimum diameter allowed if the flow is to be laminar. Minimum diameter for laminar flow. Right? So we were given that m dot equals 0.036 kilogram per second. And right now we know that rho equals 0.965 kilogram per meters cube. So we can get our Q equals m dot over rho equals 0.036 divided by 0.965, so it equals 0.0373 meters cube per second, right? So for Reynolds number, right, RE smaller than 2,300 or 2,000. So this is from another book, so I think they used 2,000. So RE equals rho VD divided by mu, right? And here, let me use 2,000 instead of 2,300. If you use 2,300 or 2,500, that's totally fine. So rho, and at the same time, V is a function of D2. So V equals pi Q over pi d squared over 4. So it equals 4q over pi d squared, right? So REC equals rho multiplied by 4q over pi d squared multiplied by d divided by mu. So it equals d and d got cancelled. So we have 4 rho q divided by pi d mu. It should equals 2000, right? So d should equals 2000 multiplied by let's put d to the right hand side. So d then 2000 needs to go to the denominator here. So it equals 4 rho q divided by 2000 pi multiplied by mu. And q we know, rho we know. 2000 is a constant, 4 is a constant, right? So pi constant, mu constant. So we know everything here. So we get our it equals 4 multiplied by 0.965, the density we calculated before, and then multiply by q is what we calculated at here, 0.0373 divided by 2000 multiplied by pi multiplied by the mu given to us, I think, is did we oh yes, we were given mu as 2.146 multiplied by 10 to the negative 5. So we have our d equals 1.068 meter. If you get any value between 0.8 to 1.2, it's good to go, because you may select a different constant. They are round up errors, so as long as you fall within this range, we're good. So the last one is question 4. So question 4 is Navier-Stokes equation, and I put a hint there. You only need to consider everything on the x direction, right? So we were given 2 board. This question is pretty comprehensive. We actually dealt with this distribution several times. We have U1 going to one direction and U2 going to another direction. So the velocity profile should look like something this. This should be your first estimation. And based on this, what it will tell you is, okay, so V and W equals 0. Because your velocity is not moving up and down between your boards. It's not going out and into the paper either. So your V and W should equal 0, right? And this will tells us, because we can use the continuity equation. Continuity equation tells us du over dx plus dv over dy plus dw over dz equals 0. And right now we see that because v equals 0 and w equals 0, so dv over dy and dw over dx equals 0. Next, we need to take a look at the continuity equation, right? So the Navier-Stokes equation. Navier-Stokes equation in x direction. So it is rho gx minus dp over dx plus mu d square u over dx square plus d square u over dy square plus d square u over dz square should equals rho du over dt plus u du over dx plus v du over dy plus w du over dz, right? So because it's incompressible, so du over dt equals 0. It doesn't change with time, it's a steady state. And at the same time, because from the continuity equation, we know du over dx equals 0. So this term becomes 0 too. And v is 0. So this term is 0 and w is 0. So this term is 0 too. So we have basically everything equals 0 on the right hand side. And right now let's take a look at the left hand side. So this is on the x direction and x is this direction, x and y, right? So the gravity's projection on the x direction is 0. So rho gx is 0. Gx equals 0. And we were also given in the description that the pressure gradient in the x direction is 0. So dp over dx is 0. And because du over dx is 0, so d square u over dx square should equal 0 too. Okay. And based on what we are seeing, our first guess of the velocity profile, that u should be a function of y, and at the same time u is not a function of z. So du over dz should go 0. Okay, the only term left is this one. And what we have is d mu d squared u over dy squared equals 0. Because mu is a constant, so we can write it off. So we have our d squared u over dy squared equals 0. And if we do integration on both ends, we will have du over dy equals c1. And if we keep doing integration to this one, we'll have our u equals c1y plus c2. You may have a question here is why we don't need to add. For example, in the first step, we put c1 here, but we are not putting f x z here. The reason is we see that because du over dx equals 0 and u is not a function of z, so theoretically your u is only a function of y. It's not related to x and z at all. So we can just treat it as a simple integration. And next we need to use the boundary conditions. When our y equals 0, we have our u equals negative u2. So that means c2 equals negative u2. Because u equals c1 multiplied by 0 plus c2 equals c2 equals negative u2. So we have c2 equals negative u2. And at y equals b, we were given the height of such a duct, right? Then we have our U equals U1. So U1 should equals C1 multiplied by B minus U2. This is our C2, right? So we have our C1 equals U1 plus U2 divided by B, right? This is our C1. So overall, we have our Y equals U1 plus U2 divided by B multiplied by Y minus U2. Okay. Based on Navier-Stokes equation and the first guess of it, we proved that the velocity profile, sorry, this should be V, velocity profile, or U, let's call it U to be consistent. U should equals to equals this one. Okay, that's a overview of our exam 3.